In this section, we're going to take a look at some applications of using exponential functions, and we're going to specifically talk about exponential growth and decay. So quantities can grow or decay at an exponential rate. Population is an example of growth, and decay of a radioactive material is an example of decay. And there are two formulas, one formula for exponential growth and one formula for exponential decay. And if you look at them, they look very similar to each other. The only difference being that the exponent on the E for exponential growth is a positive KT, and on the exponential decay, notice there's a negative in front of the KT. So that's the only difference between those two functions. So now let's talk about what each of those variables represent in those formulas. So the A of t, what each of these are set equal to, is always going to be the final amount. So I start with an initial amount and it either grows or decays, and the A of t is the final amount we end up with. The A sub naught, so this A, which looks like a sub-zero in both of these formulas, is always the initial amount that I begin with. And this initial amount is usually either provided to us or we can determine an initial amount that will work for the given situation. The K in both of these formulas, so again, the K has a positive coefficient in growth and it has a negative coefficient in decay. That K is the rate at which the substance or the population, whatever that initial amount represents, it's the rate at which it is growing or decaying. So sometimes this might be given to us as a percentage, and when we use it in the formula, we'll always want to write it as a decimal. The time is the time that we are looking at for the time span of growth or the time span for decay. So sometimes this time is given to us and sometimes that's the value that we're going to want to try to figure out. The time, whether it's days, hours, weeks, months, years, will be told to us in the problem, but if there isn't a time unit provided, then it's understood that the time is in years. So if you don't see anything in the problem specifying that time unit, then assume that it is in years. Okay, so the whole idea is to identify, we've got 4 different variables in these formulas, so we want to identify in the problem the 3 values that we've been given so that we can solve for the missing 1 value that we don't have. So you will need your calculator for this, so if you don't have that, make sure that you get that handy as we work through these problems. So let's take a look at that first example. I'm going to get rid of some of that marking there. And in this first example, we're talking about bacteria, and we've got the number of bacteria present in a culture at time t, and so this time my units on t is hours, and it obeys the given function here. So this obeys exponential growth. We can see that it's exponential growth because it's that exponential function and my base is e. So if we look at this compared to that formula, and let me just rewrite that formula. The basic formula for growth was A of t equals A naught e to the kt. So let's just identify what we've been provided in this n of t formula. So of course, n of t, this would be our final amount. Our initial amount is the number in front of the e. It's the coefficient of e. So we know that the 1,000 is representing our initial amount of bacteria that we're starting with. And then we've got our E, and then notice that the value in front of T is positive. That's because this is a growth problem and not a decay problem. But that 0.01, that's representing our growth rate. So that's the rate in which this bacteria is growing. And then, of course, you have your T for time. So let's answer these questions. The first one asks, what is the population after 4 hours? So think of what we've been given. We've been told that T is equal to 4 hours, and we are being asked for the population after that time. So what we're being asked to find is the final amount, which in this problem is represented by that n, or that n of t. So what we want to do to answer this question is figure out what n is when t is equal to 4. So in this function, we're just going to let that t in the function be 4. So notice that we are solving for the n over on the left-hand side of the equal sign, so there's no algebra involved here, it's just all arithmetic. So we just want to get on the calculator and figure out what that value is. So over on the calculator, I'm going to type it in just like it looks in the problem. So I'm going to type in my initial amount of 1,000, and then remember where your E is. So that's a second function, so I need to hit my second key first, and then my E. And this particular calculator already puts the caret there and a left parenthesis. So in that left parenthesis, I want to put the exponent, which is a product. So I want to put my 0.01 and then times the T4. And then I want to close the parenthesis. So I want to make sure that all of that is included in the exponent. So if your calculator doesn't already put that left parenthesis, make sure that you do put parenthesis around that product, the 0.01 times 4, so that the calculator knows that that entire value after you multiply is your exponent. So if I hit enter, there's my value. And so we've got 1040.81, but we're talking about bacteria here, so it does not make any sense to have a fraction of a bacteria. We just want actual full formed bacteria. So we're going to chop this off and round this off at the nearest bacteria. So we're just going to call it 1040 bacteria. And we want to make sure that we label our answer. Anytime we have a word problem, we always want to put a label on our answer. And in this case, what we came up with was the number of bacteria that would be present after 4 hours. Okay, the next part asks, when will 5,000 bacteria be present? So in this problem, we have been given the final amount. So this time we know that n is equal to 5,000, and we're being asked the question when. So that means that we're being asked to find what t is. So in our formula, if we plug in what we know that the final amount is 5,000, and we're going to use that initial amount that was provided of 1,000. E to the 0.01 and t is what we're trying to solve for. So now you just have to remember how you solve an exponential equation, where we first want to isolate the e. So that means getting rid of that 1,000. So I'm going to start by dividing both sides by 1,000. And then that's going to give me, let me move my screen up just a little bit here. That's going to give me 5 equals e to the 0.01 t. So now what we want to do is get that t out of the exponent position. So that means writing it as a logarithmic equation. So up here, I'm going to start with my exponent, 0.01 t equals the log. And again, since my base is e, the log that I'm going to use is ln, and my argument is the 5. So to solve this, I need to get t alone. So that means I'm going to take whatever the natural log of 5 is and divide by 0.01. So again, back to my calculator. I'm going to type in the natural log of 5. And here you want to make sure that you close that parenthesis, because when I divide by the 0.01, I don't want that to be part of the argument. So the parenthesis has to be closed here. Then I'm going to hit my division, then the 0.01, and I hit enter. And now this time we're talking about time, so we're going to want to round according to whatever the directions give us for the problem. Typically, if I'm not given anything, then I'm going to round to the nearest hundredth. So give yourself 2 decimal places. So this is going to be 160.94, and this was time, and in the problem, it told us that time was in hours. So I'm going to give myself that unit label of hours. So it'll take 160.94 hours in order to reach a population of 5,000 bacteria. Okay, one more question about this particular function, and this time it asks me, when will the bacteria double? So this, when we're looking at how long it takes for something to double, that is often known as doubling time, which makes sense. And doubling time is something usually that we're interested in exponential growth. So we want to find out how long it takes the initial amount to double. Now, doubling time is constant for any particular function. So what that means is it does not matter how much we start with or what that initial value is to double. The doubling time is going to be the same whether we start with 1,000, whether we start with 1,000,000, or whether we start with 1. The doubling time will be the same regardless. So when that's the case, when I'm asked for doubling time, I want to make the problem as easy on myself as I can. So I want to try to set it up where it requires the least amount of algebra. So in a doubling time problem, I am always going to let that initial amount be 1. So in a doubling time problem, if I'm letting my initial amount be 1, then that means that that final amount would have to be 2. And if I let my initial amount be 1 and my final amount be 2, it saves me 1 algebra step. So it's not saving me a ton of work, but it saves me that 1 step. So remember in this problem, I'm going to jot down real quick what that initial function looked like. So that was the initial function we were given. So instead of using this 1,000, what I'm going to do is replace that initial amount with 1, and that would make my final amount 2. So I'm going to let this final n be 2, the initial amount be 1, so that would just be an e, and I want to figure out what t is so that I know what that doubling time is. So what this means by letting that initial amount be 1 is I'm ready to go straight to the logarithmic equation. I don't have any dividing to do because I've forced this coefficient to be 1. So I'm ready to write this as a logarithmic function or equation. So I've got 0.01t, the exponent equals the log, and again it's natural log because my base is e and my argument is 2. So my time is going to be whatever the natural log of 2 is divided by 0.01. So onto my calculator, I've got the natural log of 2, and again make sure you close that parenthesis before you divide by the 0.01, and I end up with a time value of 69.31 if we go to the hundredths place, and again that time was in hours. So regardless of what the initial amount was, so even in the problem where it gave us an initial amount of 1,000, it would take 69 1/3 hours to turn that 1,000 into 2,000 or 1,000,000 into 2,000,000. So it doesn't matter what that initial amount is. Okay, so let's take a look at a decay problem. So exponential decay turns up quite a bit in radioactive material. And here in this problem, we're given the function a of t equals a naught e to the negative 0.00044 t. So notice that you've got that negative sign in front of the rate. So that's an indicator that this is a decay problem. So if we look at what everything looks like, or what everything represents here, we've got an initial amount that they tell us is 10. So I could actually rewrite this function as a of t equals 10 e to the negative 0.0044 t. So there's my initial amount filled in. And of course, my decay rate is going to be that decimal. So my decay rate is 0.00044 is my decay rate. You do not include the negative when you actually state what the decay rate is. That negative is part of that being a decay formula, but the rate itself is just the decimal without the negative sign. Okay, so the question asks how much is left after 50 years. So it's asking me for how much is left, so that's going to be my final amount. I'm being asked to find A if I know my time. So if I know that T is equal to 50. So we're just going to plug in everything we know, leave out what we don't. So we don't know what A is, and we want to figure out what that's going to be if I let that T be 50. So my decay rate along with the negative sign, and I'm going to plug 50 in for T. So again, my value that I'm solving for is alone on one side. So I'm going to just do the arithmetic and figure out what that right side equals. And I'm going to do that all on the calculator. So I'm going to type in my 10, pull up my E, and then plug in that decimal. So don't forget your negative sign, 0.00044, and that gets multiplied by 50, and I do want that included in the exponent in the parentheses because it is part of the exponent. So if I hit enter there, I get my value. So A is equal to 9.78, and if I look back in the problem, my units on the amount of radioactive material is grams. So this is going to be 9.78 grams. So after 50 years, this amount of radium didn't decrease by very much. So that's typical with radioactive material, that it takes so long for it to go away, and that's what makes it so dangerous. Okay, so in part B, we have a question that asks for the half-life of radium. Now, half-life is a time unit. So when I'm asked for half-life, I'm asked for a time. And the time that I'm being asked is the time that it takes to cut the material in half. So it's the time it takes for the material that I have to decay to exactly half the amount. So it's similar to the doubling time that we have with growth. So the comparable thing in decay is saying that we want to find a half-life. So just like with doubling time, the half-life is constant regardless of how much material I have. So if I start with 50 grams, it's going to take the same amount of time to cut that in half to 25 as it would if I started with 50,000 and wanted to cut that in half to 25,000. So when it does not matter how much I'm starting with, then that means that I'm always going to let the initial amount be 1, and that would make my final amount be a half. And again, just like it did with with doubling time, this saves us one algebra step, and once I get it set up, I'll be ready to go straight to the logarithmic equation. So let's plug these into this function here, the original function, And again, I'm not going to use the 10 for the A naught. I'm going to use the 1. So if I let my final amount be a half, my initial amount would be 1, making the coefficient of E 1. And then I'm going to use my decay rate of 0.00044, and I'm looking to solve for T. So again, because I chose the initial amount of 1, I'm ready to go straight to the logarithmic equation. So it's my exponent that equals my log, and my argument is 1/2. So that means, kind of running out of room here, T is going to be whatever the natural log of 1/2 is, divided by negative 0.00044. So on my calculator I go, natural log, and my argument is 1/2, so you can type in the fraction 1/2, or you can use the decimal point 5. And I want to divide that by negative 0.00044. So again, make sure that that division is not in the argument. You want to take the ln first and then divide. So if I hit enter, there's my value. So T is equal to 1,575.33. And again, this was time. And it didn't tell me what time, well, it did in part A. I guess it indicated that it was years. So my time is 1,575.33 years. So over 1,500 years just to cut that amount of radium in half. So not something you'd want to build your house next to. So let's take a look at a couple of more examples. And in these examples, we're going to have to do a little bit more work up front because they don't tell us quite as much information as the previous examples did. So let's take a look at example number 3. In this example, we're given the half-life of lead to be 22 years, and we want to know how long it will take for a sample of that lead to decay to 80% of its original amount. So remember, half-life is a time. So this 22 years is my time value, my T. But what I don't know is what the decay rate is. I know it takes 22 years to be cut in half, but I don't know what that decimal is, what that coefficient of T is. So remember that in a decay rate formula, we've got my final amount is equal to my initial amount times e to the negative kt. So what we don't know is what that k is. So we're going to have to start by finding that rate of decay first. So in any problem, if they don't tell me the rate of growth or the rate of decay, you're going to have to figure that out first. So since I do know the half-life, that means that I know how long it takes for an initial amount of 1 to be cut to 1/2. So I can use that to figure out my K. So I'm going to plug in that half-life T of 22 and an initial amount of 1, a final amount of 1/2, and figure out what that decay rate is. So we're ready to go straight to the logarithm. So it's my exponent equals, and I'm just going to put my 22 in front of my k like we normally do when we write a coefficient in a variable. So I've got negative 22k is equal to my logarithm, so it's natural log. My argument is 1/2. So k is going to equal whatever that natural log of 1/2 is divided by negative 22. So I'm going to divide both sides by negative 22. So k is going to equal, and give myself a little more room there. So I'm going to do on my calculator, I'm going to take the natural log of 1/2 and divide that by negative 22. And so I end up with a decay rate of 0.03150 7. We'll round that off there. So one thing you don't want to do when you are finding a rate of growth or a rate of decay that you're going to use in the problem is do not chop this off. So this problem didn't ask me to find the decay rate. If it did, then it'd be okay to say 0.03. But I want to use this decay rate in order to figure out how long it's going to take to cut it in by 20% to get 80% of the original amount. So do not round this decay rate too soon, because otherwise, if I change it to just 0.03, my answer is going to be quite a bit off. So my recommendation would be to leave at least 6 decimal places in your rate when you're going to use that rate in another part of the problem, like we are here. Okay, so now we can answer the question. The question asks, how long will it take for a sample of this substance to decay to 80% of the original amount? So that means that we're going to, again, let our initial amount be 1. So anytime they don't give me an initial amount, letting your initial amount be 1 is the easiest route to go. And my final amount is 80% of that. So 80% of 1 would be 0.8. So that's my final amount. And we're looking to figure out what the time is. And now we know what the K is. We found that here. So plugging everything in, I'm going to have a final amount of 0.8. And that equals my initial amount of 1 raised to my K. Remember to include the negative because this is a decay problem. So putting in my K, and I want to figure out what T is. So I'm ready to go straight to the logarithm. So it's my exponent, 0.031507T is equal to the log of 0.8. So T is going to equal whatever the natural log of 0.8 is, and I'm going to divide that by the negative 0.031507. And when I hit enter there, I get my time of 7.08, and my units on my time is years. So it'll take just a little over 7 years to get to 80% of its original amount. And that doesn't matter what the original amount is. It will be a little over 7 years regardless. Okay, one more example. This one dealing with growth. And again, when we read through the problem, it tells me that the population of a colony of mosquitoes obeys the law of uninhibited growth. If there are 1,000 mosquitoes initially and 1,800 after 1 day, what's the size of the colony after 3 days? And how long is it until there are 10,000 mosquitoes? I know in my backyard it seems like 30 seconds till I have 10,000 mosquitoes, but let's take a look at what this one says. So the first thing to notice is that the problem never told me what the growth rate was, what my K is. So anytime I don't know the rate of growth or the rate of decay, that's where I need to start. So I need to start first finding that growth rate. So if I start with the basic formula for exponential growth, it's A of t equals that initial amount, e to the kt. No negative in front of the k this time because this is a growth problem. So I want to figure out what k is. So that means I need a final amount, an initial amount, and a t. And it tells me in the problem that there are 1,000 mosquitoes initially, and there are 1,800 after 1 day. So I have an initial amount, a final amount, and a time for that. So that's what I'm going to plug in. So I'm going to use a final amount of 1,800, an initial amount of 1,000, and I'm looking for K, and my T is 1. So this isn't one where I can start with any initial amount because this isn't a doubling time problem. So I have a specific relationship between an initial amount and a final amount given to me in the problem. So that's what I want to use. So that means that I'm first going to have to divide out that 1,000 from both sides first, which is going to give me 1.8 equals e to the k power. So now I write it as a logarithm. So the exponent equals the natural log of 1.8. So on my calculator, I want the natural log of 1.8. And again, I'm going to use this K in the problem. So I want to make sure I do not chop this decimal off too quickly. So I'm going to go to 6 places, which would make that 0.587787 if I go 6 places. All right, so there's the K that I'm going to use in the problem. So now I can answer that first question. And the first question asks, what is the size of the colony after 3 days? So after 3 days, I want to find what that final amount is. So A is going to equal, and again, I'm going to start with my initial amount provided in the problem of 1,000. E to the, now I can use my K, 0.587787, and I want to know what happens after 3 days. So I use 3 for my T. So A is alone, so all this is arithmetic. So I'm just going to type that whole right-hand side into my calculator. So I've got 1,000, pull in my E, and my K, my rate of growth, that's not right, 0.587787, and I want to multiply that by 3, and again, I want all of that in my exponent position, so all of that goes in the parentheses, and there's my value after 3 days. I'm going to have 5,832 mosquitoes after 3 days. However you spell mosquitoes, there we go. So again, I'm not going to include any decimals here because I'm not going to count that 5,000th of a mosquito that's running around, just whole mosquitoes. Okay, so that answered that first question, and we have one more question in the problem that asks how long until there are 10,000 mosquitoes. So for the time to 10,000 mosquitoes, I'm looking for T if I have a final amount of 10,000. So 10,000 goes in for the final amount. My initial amount was 1,000. My K is still the same, 0.587787, only this time I'm looking to figure out what T is. So I'm going to divide out this 1,000 first on both sides, which leaves me 10, and then my E with its exponent, and now I'm ready to write it as a logarithm. So that exponent is equal to the natural log of 10, and now I'll get on my calculator to figure out what that is. So I need the natural log of 10, and then I want to divide out that coefficient of T. So I'm going to divide that by 0.587787, which is going to give me, my time unit in this problem was days. So I'm going to have, I'll just round to the nearest tenth, 3.9 days. So almost 4 days. and there will be 10,000 mosquitoes. Okay, so the takeaway is making sure you choose the right formula. So remember, there are two formulas that are very similar. So remember, the one for decay always has that negative in front of the K. And if you don't know what K is, if they don't tell you that in the problem, make sure you find K first before you start setting the problem up to answer the question that's being asked. Got any questions about the video, or if you run into questions in homework, make sure that you email me.